This week, we're going to talk a little bit about some probability distributions, but we are also going to focus on what's called organizing and presenting data. So you may recall that we defined statistics as the science of data, which was the collection, organization, analysis, presentation, and interpretation of data. So this week, I'd like to focus on two parts, the organization and the presentation. So far, we've talked a lot about analysis of data, putting it together in probability distributions. We talked a little bit about collection, but not really that much. But I would like to take this week to focus on organizing and on presenting our data. Now, before we jump into our material for this week, I did want to try out a joint probability example. And if you've already read it, then great. Feel free to participate. But if you haven't read it, then definitely try to participate, because I think it's a good example in showing the intuitiveness or counterintuitiveness of statistics. Also gives us a good strategy for looking at variables and determining if they are independent or not independent. So just as a review, you may recall that we talked about two random variables being independent if they met a couple of properties. You may remember those properties, but the key property, or for me the most important one, is that if the joint probability distribution of a random variable, so the f(x) of y function, is equal to the product of the marginal probability distributions, then the two variables are independent. Because what this means, right, is that the joint probability distribution is only related to the marginal probability distributions, and what the value of one variable, for example, the value of y, actually will not affect the marginal distribution of x and vice versa. So that is how we determine independence. There were other properties, but pretty much one implies the other. So I'm going to keep this here so that we know that if this property is true, then two variables are going to be independent. But now I would like to use that and see how that works. We're going to try an example called the hatching egg example. Okay, and it's a nice little example where we're going to look at different types of variables with different types of probability distributions, and we'll see if we can find a way to prove or disprove independence between the variables. Okay, so why don't we start by saying that we have n eggs. So we have n eggs. N is a random number. It could be any number, but of course, do you think n would be a discrete number or a continuous number? We have n eggs. Yeah, discrete, right? We can have one egg, we can have two eggs, three eggs. We cannot have 1.5 eggs. I mean, you can say, well, if we have an egg and a half, but that doesn't really count. Let's say we have n eggs where n is a real number. It's actually an integer, and it can be from 0 all the way to infinity. Okay. Now, each egg has a probability of hatching, okay? And that probability is going to be p. Each egg has the same probability of hatching, which is p. So my first egg has a probability p of hatching. My second egg has a probability p of hatching. My third egg has a probability p of hatching. So each egg is going to have the same probability of hatching. And remember that this is for each individual egg. Okay. Now, let's say that these eggs are independent of each other, which means that if one egg hatches, that doesn't really affect whether the next egg will or will not hatch. In other words, you can have 10 eggs hatching, but that doesn't matter. The 11th egg will still have a probability p of hatching. Okay. Now, just to do a little bit of a review, if we have n eggs, each egg has a probability of hatching p What do you think is the probability of not hatching for each egg? Yep, that's right, everyone. 1 minus p. Thank you. 1 minus p. Good. So we understand that, right? Probability of hatching is p. Probability of not hatching is 1 minus p. That's very good. All right. Now I'm going to define two random variables. I'm going to define x as the number of eggs that hatch, and I'm going to define y as the number of eggs that don't hatch. Those are my two random variables. Now, quick question. Can we find a relationship between x and y just with the information that was given? Okay, what is that relationship? Let's see, we're given some information. We have n eggs, each with a probability of hatching p.
The total, they're both going to equal the total number of eggs, because for every egg that doesn't hatch, it doesn't hatch, and all the other eggs do hatch.
Exactly, that's absolutely right, right? So we know that if x is the number of eggs that hatch and y is the number of eggs that don't hatch, then the sum should be equal to the total number of eggs, right? Eggs will either hatch or not hatch. There's no in between, right? Which means that if we have n eggs, then n should be the sum of all the eggs that hatch and all the eggs that don't hatch. Good. So we found that relationship. We get that x is equal to n minus y, or y is equal to n minus x. Keep in mind that n is a random number, okay? So we don't know what n is. N could be 0, 1, 2, 3. N is whatever number of x you have, which itself is a random variable. But anyway, x and y are related, okay, because of n, or through n. Now, first question, are x and y independent? We found a relationship between them. Are they independent or dependent? What do you think, just based on the information that's given? Okay, so I'm going to read some of the answers from the chat. Christian says the probability of each egg hatching doesn't rely on the other eggs, so independent. Some other students are also saying independent. Some other explanations, no egg affects the other chance of hatching, so independent. Whether they hatch or not, they will not affect each other, so independent. Okay, so we're saying, so far, it seems that x and y are independent. Good. And that is pretty much an intuitive way of looking at it, right? You have x, you have y, you can see that they're clearly related to each other, but you can also see that each individual egg will not affect the other one, therefore independent. But let's see if we can prove that mathematically, right? There's always a math component to statistics that we want to focus on. So let's see if we can prove this relationship, right, to show that they are independent. Remember, x is the number of eggs that hatch, y is the number of eggs that don't hatch. Now, I will give some other arguments. Actually, nobody here said any of these, so that's actually good. But some other students may say, well, x and y will have to be dependent, because if we know the number of eggs that hatch, so if we know x, then by definition we know y, which means that they are related to each other. In other words, if this one changes, this one has to change to accommodate this relationship. And it seems that one student thinks that as well. So that's good. I think both answers are seemingly intuitive. And because we have two answers that are seemingly intuitive, we're just going to have to look at the math and see if this is true. If this is true, then they are independent. If this is not true, then they are dependent. So let's see how we can look at this problem. It seems like a very easy problem, but it's actually a little bit more complex than we want to think, okay? So first off, because there's nothing stopping every egg from hatching or no egg from hatching. That's absolutely right, Jaden, that's correct. But here's the thing, if every egg hatches, then what is y? Let's say all the eggs hatch in my system, then what is y? So 0, good. Or if none of the eggs hatches, then x is 0. So it seems like there is, when one changes, the other one has to change as well. However, Brian puts a counterpoint. If one changes, it doesn't affect whether or not the next egg will hatch or not, at least during the test. Okay, so it looks like we're thinking of different parts of the example, or different parts of the experiment, which is good. One, we're focusing on how is each individual egg related to each other, which we understand that they are independent of each other. But the next is, how is the total number of eggs that hatch and don't hatch related to each other? That's really good. I like that you're thinking about this. I like that we have all these different points and counterpoints. Let's see what the math tells us, okay? So I would like to start by saying, well, we can say, okay, that we want to find the probability that x, so the number of eggs that hatch equals some value, little x, and the number of eggs that don't hatch equals some other value, little y. That's what we're looking for. We're looking for a joint probability, okay? So we're looking for the probability that x equals little x, y equals little y. Maybe another way to write this in using the joint probability notation is we're looking for f of xy, right? The probability mass function of x, little x, and little y. That's what we're looking for. If they are indeed independent, this will be equal to a function of x and times a function of y. But if they are dependent, then that means that we won't be able to separate our x's and y's into different functions because we won't have, because our marginal probability distribution will in fact depend on the other variable. So the marginal probability of x will depend on y. The marginal probability of y will depend on x. So we want to keep that in mind, that if these are independent, then this will be true. If this is not independent, this will not be true. So let's see, okay, whether or not that works. Now here, it's kind of tricky because we don't have much information other than what I gave you, right? I mean, we don't even know what n is. N is any number, you know, from 0 to infinity. All we know is that x describes, right? And let me just start using a little bit more statistical jargon here. X describes the number of successes, right, in a series of trials, and y describes the number of failures in a series of trials. I'm using those words on purpose to see if they can remind you of some important distributions. Now, because we don't know much about this, one thing we want to do, and this is an important part of Bayesian statistics or general statistics, is we can try to condition, okay, we can try to condition what we don't know on something we do know. And when I say that is, what I mean when I say that is that we can try to find a conditional probability as long as we know, right, the probability of that condition, of that conditional. And this is a strategy that I think will be helpful for you whenever you're looking at different systems, different experiments where you don't actually know all the data, but you know some of the data. And maybe you can condition your outcome as a function of the data that you do know in order to find the correct solution to a problem. My example here is that I can find the probability of x and y maybe by fixing the number of eggs. Because right now n is a random number. We could have any number of eggs n. But if n was a fixed number, we could figure out at least a relationship between x and y, right? If we fix n to some value that's already fixed, then we should be able to find some additional values for probability. So what I'm going to do, right, in terms of conditional probability, I'm going to say that I would like to find the probability that x equals some given value and y equals some other value, given, right, we're using conditional terms now, given that n equals some known value. I'm just going to call it little n. So our known values are lowercase letters, our unknown variables are uppercase letters. Okay? But how does that work? Because we need to find a way to maybe express this, okay, in terms of our final answer, which is what we're looking for. In the end, we're looking for this. I'm conditioning it, but how is this related to this? Let's think of the conditional probability equation. If I remember conditional probability, I think the probability of B given A was equal to the probability of the intersection of A and B divided by the probability of A. So if there's a way to write down the conditional probability equation for this particular expression, what would that look like? We have the probability of what? B given A, right? So how would that look like? Let's start with an easy one. What would be the denominator of the right side of the equation? The probability of A. What would that be? I would say you're close, but let's look at what this expression tells me. This says that the probability of one value given the other value, and what's under the denominator is that other value, the condition, okay? So if that's the case, oh yeah, that's good. So if that's the case, then the denominator would be the probability of the condition here. And that condition, just like Jaden said, is the probability that n equals some known value n. Good. Now, it's kind of hard to figure out what the numerator is, because how do you know the intersection between this and this? Well, really, all this is saying, right, what the numerator would be is the probability that x equals little x, y equals little y, and n equals little n. Now, that's a little bit too much to figure out, but I can just write it down. The probability that x equals little x, y equals little y, and n equals little n. Now you may be thinking that I'm trying to make this problem a little bit more complicated because we had two variables, now we have three variables, so joint probability distribution of three variables. Don't worry about it. But this is our conditional probability equation. Okay. Now the question is, how can we take this, which it seems like I just made my work a little bit harder, but how can we take this and then relate it to this? Now we're going to have to think a little bit here. We're going to have to put our thinking caps on. But let's remember a couple of things, right? Let's remember if we go back all the way to perhaps when we introduced probability, there was a rule called the total probability rule. And I'm going to give you some time to go back to your notes so you can find that total probability rule. And I'm also going to go back to my notes to find that total probability rule so we can see it here and see if there's any way we can introduce this total probability rule into our problem, because maybe that may be able to help us. So if you don't remember correctly, or sorry, if you don't remember very well and you somehow don't have it in your notes, we're going to review a bit of the total probability rule. But the idea behind the total probability rule is that you can find the probability of one event, right, by adding up the probability of that event conditioned by all the other possible events. Now that, I know it's a bit of a lot, right? But perhaps if we draw the total probability rule, we may be able to understand what that means. So I'm going to draw a little sample space here, and I'm going to make sure, I'm going to use a red pen because there's actually a little bit of an aside here. I'm going to draw my little sample space, and I'm going to say that I have a blob, and this blob represents my event B. But now I will also say that I can divide this sample space into two halves. And I'm going to call this first half. So I'm just going to, there we go. I'm going to call this first half A. Now you may remember, right, that if this is A, and then this is everything that's not A, then we can just call this A prime. So the first half of my sample space is A. The second half of my sample space is A prime. What would we call this little intersection? Well, this is the part of the blob that is both in B and in A. So this is actually going to be the intersection of B and A. And what we have here is another intersection. Can anybody tell me what this intersection would be? Let's see. This intersection is in B, right? It's part of this big blob that is B, but it's also part of A prime. That's correct, Christian. So this is going to be B cap A prime. Correct. Thank you very much, everyone. Now, the total probability rule tells me that the probability of this blob, the probability of B, is going to be equal to what? Well, we have the probability of the intersection of B and A plus the probability of the intersection of B and A prime. I think we can kind of see that graphically. It seems very simple to graph. However, we also know that we can relate intersections to conditional probabilities through the conditional probability rule, which means that instead of the intersection of B and A, what I can write is the probability of B given A, and move this to the other side, multiplied by the probability of A. So this will be probability of B given A multiplied by the probability of A. Plus, I'm going to do the same thing. I'm going to replace this using the conditional probability rule. The probability of B given A prime multiplied by the probability of A prime. And this is the total probability rule. Notice that what this is telling me is that the probability of one event is going to be equal to the sum of the intersections of that event with any other event in the sample space, with every other event in the sample space. Now, of course, this is simple because we just turned this into A and A prime. We just divided this into two events, A and A prime. But we could divide our sample space into 3. We can divide our sample space into 4. In fact, and it's what I'm going to do here, we can divide our sample space into n different parts. Okay? And what we can do is I can say, and this is a very rough drawing, so don't try to take this drawing to be for scale, but let's say that this blob is what we're trying to find. Okay? And this blue blob that I'm trying to find is essentially, right, my x equals little x and y equals little y. And we want to find the probability of that blob. Now that blob is actually spread out throughout the entire sample space. It's going to be spread out, right, through different portions of the sample space. Maybe a portion that my sample space, well, that n equals 0. A portion that n equals 1, n equals 2, and all the way up to n equals whatever the total number of eggs we could have, big N, so infinity, I guess. So what I'm doing here is I'm applying my total probability rule, okay? But instead of just dividing my sample space into 2 parts, I'm dividing it into an infinite number of parts. Actually, instead of n equals n, I'm going to say n equals infinity. Because what we're looking for is the probability that x equals little x and y equals little y. But this probability is actually spread out between the intersection of that with n equals 0, but also n equals 1, n equals 2, n equals 3, all the way to n equals infinity. So what I'm trying to get at here is that if we use the total probability rule and we apply it to this particular problem, then we could say something along the lines, and I want to be careful here because it's not exactly the same, but along the lines of, well, we have the probability that x equals little x. Oops, I should not have closed that parenthesis. Probably that x equals little x and y equals little y. Following the total probability rule, let's see if we can help me here. If we were to follow the total probability rule, but now apply it to our problem, what will we have here? What would be the first term in my equation? Let's see. In our simplified example, we look at B as the blob that we're looking for. In our particular example, The blob is simply x and y, which is what I just wrote here. Now that blob is going to be equal to the conditional probability of that blob with the first segment of my sample space, right? You can see it here, PB given A times PA, plus the conditional probability of that blob given the second segment of my sample space, PB given A prime times PA prime. Now here, instead of dividing my sample space into two segments, I'm dividing it into infinite segments. But let's just start with the first term. What do you think the first term would look like here? So what intersection am I looking for? What intersection am I looking at? Okay, so Renee says we're looking at, right, the intersection between x and y and n. Correct. And my first segment is n equals 0, right? Good. My first segment is n equals 0. So we're looking at the intersection between x and y and n equals 0. That's my first term. So we're looking here at the intersection between probability of x and y intersect with n equals 0. We'll write that in terms of a conditional probability, right? So we write that in terms of a conditional probability. What would that look like? Well, I can just follow it from here. We have the probability of my blob given my first condition. So in this case, my blob is x and y. But it's given my first condition, so my first segment of the sample space. In the first segment of the sample space, n equals 0, so given n equals 0, times the probability of the condition. And remember, the condition is simply that first segment of the sample space. And in that first segment, all we have is n equals 0. Thank you, Marco. You're very, very close, right? But remember that the next value, P of A, is actually the probability of the condition itself. And my condition is the segment of my sample space. So my sample space is divided into segments of different n values. Okay, but other than that, it's correct. Now that's the first term, right? That's the first term. The total probability rule tells me that's going to be the sum of all the terms. So I'm going to let you try to do another one. What do you think the second term would be? We're not going to do all infinite terms, but what would the second term look like? So my first term is this. My second term corresponds to the second, right? So Christian says it's the same, but with n equals 1. And that's absolutely right, right? It's going to be the same, right? The probability that x equals little x, y equals little y, given n equals 1, right? And then times the probability that n equals 1. And we are going to continue this all the way up to infinity. And that's what we're going to do. Now you're thinking of adding things and you're thinking of infinite, you may be thinking of integrals, but we actually don't have to integrate this time. We're actually going to figure out how to solve this without integrating. But our final answer, right, is going to look as follows, right? We have the probability. Oh, I got to straighten out my camera here. We're looking at the probability that x equals some value, little x, and y equals some value, little y. Now, using the total probability rule, we know that that's going to be equal to the probability that x equals x and y equals y, given that n equals 0, plus the same thing given that n equals 1, plus the same thing given that n equals 2, and so on and so forth, all the way up to infinity. So what we're looking at here is just a sum from n equals 0 to infinity of the conditional probability given, right, that n equals, well, my value n, 0, 1, 2, 3, 4, 5, all the way to infinity, times the probability that n equals my value, 0, 1, 2, 3, all the way up to infinity. So what we're doing here is we're using the total probability rule in order to find an expression for our unknown probability in terms that we may be able to understand, which is here. Okay, so that's essentially what we are looking at. Now, I know we're basically going back to all of our basics, right? Trying to come up with new expressions based on the very, very basic statements of statistics. But I want to make sure that we're all on the same page. So before I move on, are there any questions? All right, no questions, that's good. Now, this seems like it's gonna take us a long time to solve because we have to add up n all the way up to infinity, right? But here's the thing, we have some data that was given to us, and we could probably try to use that data to maybe simplify our work. This is what Joe Blitzstein, he's a professor of statistics at Harvard, this is what he calls thinking concretely, right? I would just say this is just trying to make our work easier, right? Just using a bit of critical thinking to make our work a little bit easier. So let's see if we can use our given information, right, in order to find a way to simplify this sum, to make this sum a little bit more bearable. I'm gonna summarize our given information. I know we had n eggs. We had probability of hatching P. And let's say, right, let's say that hatching corresponds to my success, okay? Just to use statistical terms, okay? Now, because we have probability of hatching P, and let me focus this a little bit more. Because we have probability of hatching P, then we also know the probability of not hatching is going to be 1 minus P. And I gotta straighten out my camera again. We know that eggs are independent. And we know that X is the number of eggs that hatch. And we know that Y is the number of eggs that don't hatch. I think that's all that was given to us. We found out some relationships. I think Renee figured out that X plus Y would equal N. So that's all our given information. Now with this given information, we want to find a way to solve this expression where the probability of X and Y equals, right, the sum of the conditional probability of X and Y given that N equals some number times the probability that N equals some number. And that number is going to be from 0 all the way to infinity. So let's see. Let's see if we can find a way to simplify this. So I'm going to ask some questions. Hopefully, if we understand the problem, we'll be able to answer them. If not, it's okay. We'll understand eventually. My first question would be, and I would like for you to give me a number. And if you think it's impossible to calculate this number, then I will recommend that you check the given information again. I would like to know what is the conditional probability, right? The probability that X equals 3 and Y equals 5, given that N equals 10. What's that probability? 0. Why is it 0? Exactly, right? We need 10 eggs, right? If we need 10 eggs, here we say that we only have 8, right? 3 hatches, 5 don't hatch. That total number is 8, but we know that X plus Y has to equal N, which means that this conditional probability is actually going to be 0. And that's going to happen for any combination of X and Y that doesn't add up to our given N value, which means that we are, even though this is an infinite sum, we're actually simplifying that sum a lot, right? A lot. Good. So basically in any combination, right, where X and Y doesn't equal N, which there's infinite combinations, right? Then that probability, that conditional probability is going to be 0. We can also say that the only time the probability is not 0 is when X and Y equals N. So what I can do now is I can say that my probability is not 0 only, right? Only when n is equal to x plus y. That's all it is, right? When n equals x plus y, it's not 0. When n equals something else, the probability has to be 0, right? Because x plus y has to equal 0. That's the total number of x. So because I already know that n has to equal x plus y, I can actually reframe this equation in terms of x and y instead of in terms of the little n. So that's what I'm going to do now. I'm going to say that the probability that x equals some value little x and y equals some value little y is actually going to be equal to the probability, or the conditional probability, that x equals little x and y equals little y, given that n equals x plus y. And of course, times the probability that n equals x plus y. That's it. And I've simplified what seemed to be an infinite sum. I've kind of simplified it into just one expression, right? Because now we know that if I modify x and modify y, so if I pick two values of x and y, probability really only exists for the point where n equals x plus y. And because I want to find the probability for two values x and y, so those two values are going to be what I'm looking at, what my distribution is showing, then I know that probability only exists for the case that n equals x plus y. So I don't have to add up infinity, right? I don't have to add up n equals 0 to infinity. I only need the value when n equals x plus y. So far, does all that make sense? Or do we need to maybe explain a little bit more?
Couldn't x plus y equal infinity or no? Because
Well, you can say like if x or if y equals infinity, right? But right now, the important part is that even if one of these two were equal to infinity, that it's still just one expression, right? Because we can still find n by taking one value and adding up the other. So good
Gotcha.
question. I would say it's still one expression. Right. Thank you. Good. Good. And here's the thing, right? We can make this even better, right? Because by definition, you think about it, by definition, if x is the number of hatching eggs and y is the number of eggs that don't hatch, if we know the number of hatching eggs, then by definition, we know the eggs that don't hatch, right? We know that eggs are not going to hatch. So if we know that x is the number of hatching eggs, then by definition, y will be the number of eggs that don't hatch. Now, what that means is that y is actually redundant in our conditional probability equation. And that's actually really, really nice that y is redundant. Because by definition, right, if x equals little x, by definition, y has to equal little y because n equals x plus y. So what that means is that we can take this probability, and we know that there's a relationship, a clear relationship between x and y. And because there's a clear relationship, then my y simply becomes redundant, not necessary. This is simply the probability that x equals little x, given that n equals x plus y. Because notice that with these two statements, I'm already telling you everything I need to know about the problem. If you can throw any number, right? Let's say x equals 2, n equals 10. Let's say that's the number. If x equals 2 and n equals 10, do I know why? I'm asking like why as in the question. I'm asking like, do I know the variable y? Yes, right? Y has to equal 8. So because if you know x and you know n, you already know y just becomes redundant, then it doesn't really matter. You don't have to include it here. Because if x equals x and n equals x plus y, then by definition, y has to equal this value. So it's redundant. We can take it on and simplify our expressions just a little bit more. The lowercase letters are the lowercase letters are known values, and then uppercase letters are always the random variable, which can be any value. Yep, that's correct, Carlos. That's just, by the way, statistical notation. I don't particularly enjoy it, but it is statistical notation. We use lowercase values for known values and uppercase letters for variables. And variables can be any number of values. Good. So we have something interesting, right? We can see, okay, that we have a probability distribution of hatching X. And now I would like to see if there's a way we can figure out, okay, how these probability distributions, or what these probability distributions would look like. Okay, so you may want to go back to your notes on our initial probability distributions, but I want to start with this first term. I want to start with the first term. My first term is the probability that X equals some value X, given that N equals some known value. So what am I looking at here? Well, each egg, right, can be taken to be a trial, right? It's a trial. So if we have an experiment with multiple trials, each egg hatching or not hatching trial, we can say that success is defined if the egg hatches. So each egg is a trial, and each egg that hatches is a success. So if each egg is a trial, that means that N is the number of trials. And you can see that it's a fixed value, X plus Y. So it's a known value, right? So we have a fixed number of trials, and X is the number of successes in that trial. So what type of probability distribution does this have? Well, we have a fixed number of trials, and my random variable is the number of successes of those fixed number of trials. Does anybody remember what type of probability distribution this is? You're gonna have to go back to your notes, and I'm gonna give you time to go through your notes. Oh, yeah, you got it, Marco. Binomial distribution, that's correct. The binomial distribution, right, is the probability distribution of a variable that represents the number of successes, right? The number of successes in a sequence of trials where each trial has the same probability of success P. That's the binomial distribution. You may remember the binomial distribution, but if you don't, I'm going to write it here just so you can have a bit of a refresher, right? The binomial distribution, the probability of success or number of successes X was going to be equal to N choose X times P to the power of X times 1 minus P to the power of N minus X. You may recall this binomial distribution, right? Where X is the number of successes in your experiment, N is the number of trials, and P was the probability of success. 1 minus P is the probability of failure. This is the binomial distribution. So if this is a binomial distribution, let's just write it down, right? We already know that X is just little x, and we know that N is actually going to be X plus Y. So if I write it down with my given variables, I have, well, instead of N, I have X plus Y. So I have X plus Y, choose X. And we have P to the power of X. P is already given, the probability of hatching. And that is elevated to the power of successes X. And then I have 1 minus P to the power of N minus X. So to the power of N, so X plus Y, minus X. So what is that going to be equal to? N minus X, where N is equal to X plus Y, just Y. That's correct. That's absolutely right. Thank you, everyone. Good. And we can solve this. I'm actually going to expand this binomial coefficient because you'll see that expanding it allows us to simplify even more in the future. So a bit of a spoiler there. Expand this binomial coefficient just a little bit more. We know that X plus Y choose X is going to be equal to X plus Y factorial divided by X factorial times X plus Y minus X factorial. But X plus Y minus X is simply Y. So Y factorial. Correct. Thank you, Renee. Good. So we have this, and then we have P to the X, Y minus P to the Y. Good. Absolutely correct. Good. Now we got to figure out what this second term corresponds to. Now this one's a little bit harder to understand intuitively, so I may just give you the solution. But we do need to understand, okay, that n can be any number as long as the number is x plus y. So what we're looking at here is in a sequence, and maybe not even a sequence, maybe I'm going to use a different word. In an interval, of all the possible values of n, so n equals 0 all the way to n equals infinity. In that interval, n, right, or what we call a success, is when n equals x plus y. But that, okay, only occurs over a series, right, of intervals. Here n equals x plus y, here n equals x plus y, here n equals x plus y, and everywhere else n does not equal x plus y. And of course, these intervals are dictated by what value of x and y I choose. So let's think about it this way. If we are looking for the interval, okay, if we're looking for the interval, right, between each success, what type of probability are we looking at? Are we looking for? When we talk about intervals, no longer trials, now we're looking at intervals. It could be time, it could be length, but they're intervals. Do you remember what type of process this was called, or what type of probability distribution it had? Poisson, that's correct. That's absolutely right. Thank you, Marco and Sarah. Good. So if we're looking at intervals, then this is a Poisson process, which will have a Poisson distribution. So if you don't remember the Poisson distribution, that's fine. We are going to recap it here. Here, we're saying that the probability of n, let's just call this little n, right, which is x plus y, is going to follow a Poisson distribution, which is e to the negative lambda t, if I remember correctly, times lambda t to the power of n, divided by n factorial. But here's the fun part. My interval really is a unit interval. Now, why is my, oh, I should just draw the whole thing. Now, why is my interval a unit interval? Because once you choose n and once you choose x and y, once you know what x and y are, then there is only one value of n through my entire space, one possible value of n. If x is 2, y is 5, n has to be 7. It cannot be anything else. So that means that over an entire interval of just 1, so over one entire interval, we can find what n is. So by selecting t equals to 1, right, my interval equals to 1, I can further simplify this a little bit more, right? We have e to the negative lambda, t equals 1, so I don't have to worry about it. We have lambda, t equals 1, so to the power of n, but we know that n equals x plus y, so lambda to the power of x plus y. And this is divided by n factorial, but n is x plus y. Okay? I love this example, and you can see why I love this example, right? We've covered total probability rule, conditional probability, binomial distribution, Poisson distribution. We've pretty much covered more than half of the class already. So we found the two probability distributions for my term. Now let's see what this probability ends up becoming. So let's combine the two and maybe use a little bit of math to see what this ends up being. So we have probability that x equals some value little x and y equals some value little y is going to be equal to, we have our binomial distribution, times we have our Poisson distribution. A little bit of math here. X plus y factorial cancels out with x plus y factorial. So far, so good. I can, write this a little bit differently. I'm just going to put everything in my numerator, everything in my denominator. So let's see what I have in my numerator, p to the power of x, 1 minus p to the power of y, e to the power of negative lambda, lambda x plus y, or lambda to the power of x plus y. Okay. I've canceled out my x plus y factorial, but I still have x factorial, y factorial. Good. I'd like to do a little bit more here, just to rearrange it a little bit, because remember, the end goal in the end, what we're trying to see is if we can prove this. So in order to figure out if we can prove this, I have this little lambda to the power of x plus y, which is not very helpful to prove what I want to prove. So instead, I'm going to say, well, just using a little bit of what we know about exponents, lambda x plus y should be equal to lambda to the power of x times lambda to the power of y. Is that correct? Before I make a fool out of myself, is that correct? X, right? The same term, right? Elevated to a power is just like the sum of the powers. Good. Good. All right. So if I write that down, okay, then I'm going to end up with the same expression, lambda x, lambda to the power of y. What I would like to do now is I'd like to put all of my x's on one side, all of my y's on the other side, or at least within the same term, right? All of my x's first, and then all of my y's later. So what do I have? Let's see. I have p to the power of x. I have lambda to the power of x. What else do I have? I have, well, I guess I have in the denominator x factorial. I have 1 minus p to the power of y. I have lambda to the power of y. And I have y factorial. And then I have this lonely e to the negative lambda in there, kind of trying to find a spot. But it's okay, because what I'm going to do now is I'm going to be a little bit creative. Once again, I'm going to bring in my little high school knowledge of mathematics and say, well, e to the negative lambda, I think we can agree that e to the negative lambda is equal to e to the negative lambda p times e to the negative lambda 1 minus p. Is this correct or not? And you can use this as a guide to see if this is correct. Let's see, if we multiply e to the negative lambda p times e to the negative lambda times 1 minus p, is that going to give us e to the negative lambda? Yeah, because when you multiply, you add up the exponents, right? And when you add up the exponents, notice that you have p, and you are adding 1 minus p to that. Or in this case, negative p, you're subtracting negative 1 minus p. You're subtracting 1 minus p, which is still going to be the same, right? P plus 1 minus p is equal to 1. I mean, you don't have to know anything about probability. This is just standard, right? P plus 1 minus p is just equal to 1. Okay. So what I'm going to do this so that I can split this little e here, this lonely e, into a success e and a failure e. So what that ends up looking like, let's see, e's. Well, I have e to the negative lambda p. Then I had, let's see here, I had p to the x, lambda to the x. Well, they're both elevated to the same exponent, so that's just the same as saying lambda p to the power of x, and this divided by x factorial. And then I have e to the negative lambda 1 minus p. And now I had lambda, here we go, lambda y, and 1 minus p to the power of y. So I can write this down as lambda times 1 minus p, elevated to the power of y, and then divided by y factorial. Ooh, I gotta be careful. This is not part of the exponent. This is the exponent. Okay, I'm just gonna do this. And why did I want to do this? Well, look at it this way. We're looking for the joint probability of x and y. And we've noticed that this joint probability can be expressed as a function. Okay, what this is a function of x, because it gives me the random variable x, but it also deals with the probability of success, the probability of x occurring. So this is a marginal probability distribution for x. Notice that it relates to the variable x, and it relates to the probability of that variable occurring, the probability of success. And now here, what we have is an expression for the marginal probability of y. Notice that it relates to y, and then it relates to the probability of y occurring. Remember, y was x not hatching, and y minus p, 1 minus p is the probability of x not hatching. So this is a perfect example, right, of a marginal probability for y, because it gives me the variable and the probability for that variable occurring. Variable and probability for the variable. So what we have here is we have a joint probability that we've now been able to express as the product of a marginal probability. So are x and y independent, or are they dependent? Independent, right? Because we have just shown that the joint probability distribution is actually equal to the product of the marginal probabilities of both. So good job. I think this is actually a pretty good review of, the first 8 modules of the class. So good job there. And we've been able to show that even though x and y are related, even though x and y are related by this, they're still independent, at least mathematically independent. On the chat, we have, what a wild ride for something that seems so simple. I know, right? Can you imagine that this would be on the test? Just like give you the example, prove that x and y are independent. You'd be like, wow, this is easy. And on the chat we have, so we did binomial and then Poisson. Why did we multiply those results together? Well, because what we had here, right, our expression that we got was that the probability was equal to this conditional probability, the probability of x equals x, well, let me just write here, given n equals x plus y, times this Poisson probability, the probability that n equals x plus y. So they're already multiplied. I just tried to do these separately so that we could understand that this is binomial, this is Poisson. Even though they're part of the same system, they're part of the same experiment, this part is binomial and this part is Poisson. We have been able to show that the number of eggs that hatch is independent from the number of eggs that don't hatch. As counterintuitive as that may seem, that is what the math shows us. And the reason why this happens is because n, right, the number of total eggs is a Poisson process. So if n is a Poisson process, then x and y are both going to be Poisson variables. And you can see it here, right? Both marginal probabilities are actually Poisson probability distributions, which means that because they are both Poisson variables, they are independent, and we can see it here in this example. I think it's a good place to take a break because we are going to start a bit of a new topic, and I think I would prefer that we take some break to relax and just, recover from this interesting yet very, very, very crazy experiment. Okay, let's take a break and we'll meet. It's 3:06. We'll meet at 3:20.